Thank you everyone for attending this next in our series of product-focused webinars. Today we have a guest speaker, which I think is going to be extremely interesting with some new computer developments. So we've titled this webinar today, The Science of Reaction Mixing, Seeing What You've Been Missing. So hopefully over the course of this short webinar, we can give you a really good introduction into the Kineticolor software platform that will help you with your workflows. So I'm just going to share my screen, so just bear with me 2 seconds. So today we're going to be talking about the Kineticolor software platform and how that can turn video inputs from any camera into decision-ready images to allow you to monitor your reaction process, your chemical process. So whether you're looking to integrate multiple applications or improve your current process, hopefully this webinar will give you some practical insights into some real-world examples of how this software platform can simplify your workflow and increase your efficiency. So we'll show you also some performance data against our magnetically coupled overhead stirrer, which is a bonus. But the real emphasis is on the software control here. So throughout the webinar, if you have any questions, please enter them into the chat function. We'll have plenty of time for question and answers at the end. So yeah, if I could ask you to add that into the chat function. So this is what we're here for today, the Kineticolor video analysis software. So a brief introduction to what Kineticolor is. So as I said, Kineticolor turns video from cameras into decision-ready insights into your chemical process, allows you to monitor your process. So the software uses computer vision to quantify what the eye sees. So whether that's changing color, texture, mixing, shape in your chemistry bulk, in your reaction. And with that, you can monitor your reactions, you can monitor mixing, separations, and electrochemistry applications without needing to touch the process. So this is built for us, for our audience here, for scientists, from lab to plant. It's size exclusive. And Kineticolor is non-contact. It's hardware agnostic and it's scalable. It allows you to analyze multiple regions within a single vessel. It's extremely powerful. And as it's one view, you can also use this for looking at high throughput experiment workflows as well. So we have a guest speaker today, Dr. Mark Reed. Mark will be demonstrating with some video and his presentation, the novel Kineticolor non-invasive computer vision software. As I said, this offers lots of insights into our chemical reactions. So as once, a brief introduction to Mark. There's a whole history of Mark's, a whole line of history of Mark's experience here. Mark got his master's and PhD at the University of Strathclyde and did postdoc at University of Edinburgh. In 2016, Mark got a prestigious Leverhulme Early Career Fellowship and rejoined the Department of Pure and Applied Chemistry back in Strathclyde. Mark's been at Strathclyde for a while. He is the CPAC-sponsored research fellow and is a lecturer for innovation and education at the University of Bristol as well. So quite prestigious titles. So Mark recently got the UKRI Future Leader Fellowship and is working still in the Department of Chemistry at the University of Strathclyde. So amongst other things, Mark's interest covers a whole range of different chemistry applications, but to keep this short, Mark is the inspiration for Kineticolor, which is what we're here for today. So I'm going to hand the webinar over to Mark, who will give us some insights and tell us a little bit more about the Kineticolor software platform. So over to you, Mark.
Thanks again for having me along, and thanks indeed to everyone who's made the time to be with us on the call today. As someone who grew up as a physical organic chemist, I want to share with you a story today of how Kineticolor was, before it was ever invented to serve industry, was very much a personal itch to scratch in terms of adding another process monitoring tool to the bag that we needed many years ago and didn't have at the time. Today, we'll focus on a story of how you can use cameras to understand mixing, even on the lab scale. Sometimes we defer mixing to scale up in manufacturing, but today's story is about how you can point cameras at processes in the lab and understand the subtle but very important distinction in mixing between vessels and how mixing is achieved in those vessels. Before we get to that, a little bit more of a historical introduction. As I said, I grew up as a physical organic chemist, and that's what my academic research team has been rooted in. And for many years, as many on the call will also have done, we monitored processes in many ways that won't be of a surprise to you, using probe-based technologies like IR-based probes or UV-based probes, or other sampling methods like using HPLC or using online NMR techniques. But as we were doing this and getting our research team started, a series of serendipitous conversations led to a really provocative series of questions asked of our team. What if I want to monitor processes like these without touching them? What if I put a probe into my reaction and that probe actually changes what's going on? What if the probe becomes blind to what's going on in the reaction? In other words, how can I look at my chemical process without touching it? And it was in a series of short events thereafter that we pivoted our entire research team to thinking about this gap in process monitoring. How might we invent methods that look not from the inside out with well-established probe-based technologies, but how might we look from the outside in at the reaction bulk using camera-based technologies? And it was these questions that then led to Kineticolor being invented. What comes from that is a process of being able to turn video data like this one on the left-hand side into time-resolved kinetic information on the right-hand side. And what you can see here in this time-resolved plot is an example of how we can look at two areas within the same reaction vessel and plot the difference in the rate of colour change over time. We'll get into what the metrics mean, but all you need to see right now is that we're looking at two different areas of the same vessel and showing that mixing occurs at different rates in those different parts of the same vessel. All of this message today and the stories that I'm telling you, if you forget most of it, the key message to remember for you and to think about your own processes is that it's very much possible now to take a video of what you do, use software and turn it into kinetic information. What you see can be turned into numbers that you can use. So to begin that, we have to first look at how is it that we take what we see by eye and turn it into numbers that we can use. And in computer vision, there are a number of very well-known colour spaces that help us quantify and digitalize the colours that are recorded on a camera. And in the interest of time, I'm focusing only on one of these colour models today, the so-called LAB colour model. And to help us understand why that's useful in quantifying chemical kinetics of the bulk, focus your eye on this little data point here. Now, this can be a colour taken at the start of a video. And what we're doing here is quantifying that colour on this LAB space with the L axis denoting lightness, 0 is pitch black, 100 is bright white. The A axis covers a spectrum of colours from green through to red. And finally, the B axis captures colours on a spectrum from blue through to yellow. So if this colour here is at the beginning of the video, we can imagine following the chemical process as it changes colour over time. And the quantification of that colour change can be captured using the LAB colour space. And you can see this dashed line between these data points is showing the ever increasing change in colour versus the beginning of the video. And if you look at the inset on the right-hand side here, when you plot those so-called delta E measurements over time, we then build up a kinetic picture of what is going on in the reaction bulk. Remember, this delta E metric here was subtly mentioned earlier as a change in colour. The higher the number is on this y-axis, the more the colour has changed since the beginning of the video. And it's this dashed line here that we call delta E. And I can go into much more detail on that later, but this is one of the key exemplar metrics we can use to turn what we see by eye into numbers that we can use. So a fairly simple practical example, but again, mixing focused for today's webinar in the first case. What you're going to see is two short videos playing out side by side here. One of these reactors has a baffle cage in the beaker, the other one does not. They're both stirred in the same way at the same rate, and we're going to see the injection of a base to trigger the colour change in a pH indicator. But what I want you to keep your eye on is this little white rectangle that's just underneath the impeller in both videos. So as I now play both videos together, you should hopefully see that you're getting that colourless to magenta or purple colour change. But more interestingly, even as I speak, hopefully you can see that the colour change has stabilised far more quickly on the video on the left-hand side than it has on the video on the right-hand side, where the mixing and the colour change is still taking place even as I speak over it. We can use these video data as input for Kineticolor software and plot these changes in colour using this delta E metric once again. So the higher the number on the y-axis, the more the colour has changed since the beginning of the video. And what we can see here is that the video on the left-hand side leads to a stabilisation of the colour far more quickly than the video on the right-hand side. And as for anyone who's a beginner in understanding mixing and quantifying mixing in a chemical process, you can use these times derived from the stabilisation of the colour change as an indication of overall mixing time. And in this case, the shorter the time, what we can infer there is that the mixing is more effective in the vessel on the left than it is on the right. So we've quantified what we see by eye and turned it into numbers that we can use to understand the differences in mixing in each case. To give you a slightly more complex example, we've used and published on the Villimo-Dushman class of reactions, which set up a pair of competing reactions which are triggered by the addition of hydrochloric acid into an aqueous solution of potassium iodide, potassium periodate, and sodium hydroxide. The important thing to remember here is that if this reaction is triggered and the mixing is really, really effective, or we get so-called good mixing, what we get is a neutralization process which remains largely colourless. However, if the hydrochloric acid is injected into this mixture and the mixing and the stirring is not very effective, we get high local concentrations of hydrochloric acid, and that leads to a side reaction that produces iodine. So rather than going from colourless to colourless, we have a process that goes from colourless to yellowy brown. So the more coloration in this reaction, the more we get a signal that mixing is not as good as it could be. If you look at this process through computational fluid dynamics and look at the sorts of tank reactors that we're interested in, some of which we've used from Asynt directly, we can model those reactors and look at what is the amount of power exerted by the overhead stirrer at various cross-sectional areas of the tank reactor itself. And for the uninitiated chemical engineers in the room, all we have to understand today is that the red portions denote a higher power exerted per unit area from the impeller, and the bluer areas higher up the vessel towards the surface show that the impeller and the mixing is not as effective at the surface as it is close to the impeller. So if we had to ask where in the reactor should we inject the hydrochloric acid, if you want good mixing, models like these ones make it clear that you shouldn't actually inject from the surface, but you should try to inject the hydrochloric acid from as close to the impeller as possible. Now, these are computational models, but we can use Kineticolor to help verify the likes of these CFD models. And what you can see now on the left-hand side are 3 videos showing the hydrochloric acid being injected from the surface, from the midpoint of the reactor, and from the point closest to the impeller. And as you can see by eye here, the amount of yellowing or browning caused by iodine formation is far more severe on the left-hand side when the hydrochloric acid is injected at the surface, compared to what you see when you inject the hydrochloric acid from near the impeller. So what we see here in these videos is firstly consistent with that CFD model, but we can go one step further and quantify those data by using the video as input for Kineticolor software. In this case, to give you a different example of a metric, rather than delta E for color change, we can use this B star metric. And what does that mean? This is a measure of yellowing in the positive Y dimension. So the higher the number in this case, the more the process is yellowing over time. And therefore we can infer that more and more iodine has been formed over time. So if we look at this firstly for the example where the hydrochloric acid was injected near the impeller where mixing is most effective, we only see a modest amount of yellowing over time. Compare that to the case where we inject the hydrochloric acid not from the impeller zone, but from slightly further up the reactor around the midpoint. We can see in this case here quantification of more yellowing than for the impeller zone addition. And finally, we can show the case for the most severe form of bad mixing where the hydrochloric acid is injected from the surface. And we can see here the B star metric more and more positive as we get more and more yellowing. So this helps us quantify this case of poor mixing versus more effective mixing for the impeller zone addition. So once again, this is another bit of a story that says what we take in as raw data is video. We point a simple camera at a chemical process and we use Kineticolor software to turn those data into kinetic information of the reaction bulk that we can use. To take this closer to how we came to collaborate with Asynt more recently, I'll share a little bit of a study that we published recently in ACS Sustainable Chemistry and Engineering, where we asked, how can we quantify mixing in highly viscous solvents, and what is the impact of switching to a highly viscous solvent on the organic synthesis that we want to achieve in those sustainable solvents? So to give you a short version of that story, what we're going to show here is mixing in something like methanol on the left-hand side, which is a petroleum-based solvent, and it might be a solvent that we want to replace by a more sustainable urea-based deep eutectic solvent, which is highly viscous compared to methanol. How can we show that by eye? Well, let's look at the simple process of injecting a dye into the methanol reactor on the left-hand side. So if I play that video now, you can see that a dye is injected and we get to a state of homogeneity really rather rapidly. If we then take that video and quantify it using the color change metric delta E that we introduced earlier, we can see here that over time we get a rapid rise in delta E, a rapid change in color which stabilizes within tens of seconds. Now look at the video that's about to play on the right-hand side for the same dye injected into the viscous deep eutectic solvent. You can see in this case here that mixing takes much, much longer and we don't reach homogeneity in the short time that I show that clip and narrate it to you. So if we then convert that video into the color change data versus time in the form of this delta E metric, you can see very clearly in a more quantified sense now that the mixing time is far more elongated in the viscous solvent versus the non-viscous solvent. So this might seem trivial on the surface, but if we replace the non-viscous solvent with a viscous solvent in the name of sustainability, we have to understand how this can impact the downstream organic synthesis that's taking place in such a viscous solvent. And just before we get there, let's have a look at some of the reactors that we might choose to develop a reaction in. A simple lab scale Schlenk tube, first of all, we can once again look at computational fluid dynamics models of these systems and how they're stirred with traditional stirrer bars. And as you can see again here, the power exerted by the stirrer is most concentrated near the stirrer itself, and this dissipates rather quickly, especially in a viscous solvent as you approach the surface of the vessel. So watch what that looks like in real life for this dye injected into the Schlenk tube here holding a deep eutectic solvent. You can see in the time that I'm narrating here that mixing is reaching homogeneity around the stirrer, but it's far more sluggish as you approach the surface of the Schlenk tube. And important for mixing and Kineticolor, it's not simply a case of pointing at one region of interest and quantifying the colour change over time. We can look at multiple regions to understand the spatially resolved impact on mixing for different cases. So if we look at region A in this example, we see a rather sluggish evolution of the colour change, and it stabilises in the order of hundreds of seconds. Whereas if we look at region B near the stirrer bar, we see a far more rapid rise in delta E and a quicker stabilisation of colour consistent with the CFD model on the left. You can then go a step further and think about, well, what if I made a choice to use not a Schlenk tube, but a round bottom flask? So the CFD model in this case suggests that with all other things being equal, the power exerted by the stirrer bar reaches a far wider cross-sectional area of the reactor than versus the Schlenk tube. But still, let's look at the video of what that looks like in real life. So the mixing does indeed start to homogenize around the stirrer bar really rapidly, but you can see that towards the edges of the reaction volume, it's still taking a long time for the dye to dissipate out to the edges, and this again is consistent with what we modelled by CFD. But now let's take a step further and verify that model quantitatively and experimentally using Kineticolor analysis of such a video. Here, if we analyse region A, we can see a rapid change in colour and stabilisation through this delta E metric. And if we look at region B, we can see that it's a far slower evolution of colour change out towards the edge of the reactor, once again consistent with the CFD model. So if we compare those together and then think, how does this actually impact a reaction that is highly dependent on mixing? So if we look at solid liquid mixing in the case of this aldehyde reduction, we can see in that the more poorly mixed narrow Schlenk tube reactor, we have a relatively low conversion from the aldehyde to the primary alcohol. But when we move to the wider vessel and the more effectively mixed round bottom flask, all of a sudden conversion rises rapidly. And all of this is based on changes in the mixing profile more so than changes in the chemical conditions of that reaction. So to bring this to the third and final story, this now gets us to a stage where after developing this understanding of mixing with Kineticolor, we had the opportunity to consider how might we understand mixing profiles in some of Asynt's apparatus with the detailed efforts that they're taking to understand how to improve mixing on a lab scale, all once again anchored on taking video data in and producing bulk kinetics as the output. So the way that we did that was to once again firstly focus on a simplified dye injection process where we compared a stirred solution versus the mini-spin impeller-based stirring system. And after injection of that dye, record a video to see how long does it take for that dye to homogenize throughout a viscous liquid. We then use the video file and Kineticolor software to quantify what we see by eye and through the video. And using those data, derive mixing times to understand which system leads to faster mixing and homogenization more quickly than the other system. So that was the question that we asked. In order to do that, I'll show you one example of a video output on this slide here. On the left-hand side, you see a video of the stirrer bar based system with a viscous deep eutectic solvent as before, and a stirrer bar, which you can't see in this vantage point. And on the right-hand side is the equivalent case of not using a stirrer bar, but using the mini-spin system in its place. And if we use the likes of the delta E metric, which I have exemplified for today's webinar, we can extract the quantifiable information from those videos. And what we see in a larger suite of data, as exemplified here, is that the red data for the mini spin stabilizes and the color changes much more rapidly than for the stirred system, which is more erratic for a longer period of time. When we summarize what we did on a grander scale of the full suite of reactions and dye injection processes that we looked at here, when we compare the mixing time for the mini spin system versus the equivalent stirrer bar system, we saw that across temperatures, the stirred system had much longer mixing times than for the equivalent case in the mini spin, and all things become equal when we get to higher temperatures where the viscosity impact of the deep eutectic solvent is minimized. But one more time, through those three stories that I've shared with you today, what you want to be thinking about as well as mixing is, how might I point a camera at my process? How might I get a video and turn what I see by eye into kinetics of the bulk that I can use to understand, or perhaps even to optimize the system that I care about? What I've shared with you in this short webinar is using 2 of 4 major modules within Kineticolor software, the core color-based analysis and some elements of the mixing algorithms in the Kineticolor software as well. In our broader published works, there's even more detail and more sensitive mixing metrics that I've not exemplified today that can understand mixing in processes that are harder and harder to see in cases where the reaction might be near opaque, for example. We also have processes where we've looked at parallel reactions, as Andrew mentioned at the beginning, and we're starting to look at how we can use Kineticolor to understand chemistries that are most important factor is a change in shape of a material over time, more so than the change of a colour or a mixing profile over time. For now, I'll leave you with the thought that if you're interested in learning more about Kineticolor, you can reach out to us via the website, and you can find us via the papers that I've cited here today. And if you're interested in getting hands-on and seeing a demonstration of the software itself, how you can take your videos in one side and get your kinetics out the other side, you can also reach out to us via the website and arrange that demonstration.
So we've seen how the Kineticolor software can help us understand different mixing regimes. And you can see that within different vessels, we have different mixing with baffles and impellers. We can have different mixing compared with traditional magnetic stirrers. And you can see that in the instant with the slank tube, the round bottom flask gave better mixing. So there's a place for different regimes within our chemistry. But we've also seen that the rate of mixing is very important in our reaction for selectivity, byproduct formations, and reproducibility. You know, mixing is chaotic, it's turbulent in its nature. If we can increase mixing, we can have better control of our reactions. And that's a key design in how we are preparing our chemical reaction. And as we've seen, with more viscous material and maybe the introduction of solids, we need better mixing to get our desired outcome of our reaction. So where viscosity matters and where we have solids that might be damaged by magnetic stirrers, and I'm going to be talking about the dry syn mini spin just briefly, but magnetic stirring still has a place within our chemistry, and as we've seen, elevated temperatures reduce that differential between different mixing methods. So increased temperature reduces viscosity. So overhead stirring has predominantly been the domain of larger volumes in the kind of process area. But we haven't really had access to very good overhead stirring on a laboratory scale, on a research scale, which is where the mini spin comes in. And we've seen how the mini spin can impact mixing compared with a magnetic stirrer for those viscous materials. So I just wanted to introduce the mini spin. The mini spin is an overhead magnetically coupled stirring system for small scales. And as you can see, it's designed to meet all of the requirements we need in a modern laboratory. So it's highly chemically resistant. It's very easy to set up. We can use the magnetically coupled driver for one or up to four different vials. We have different capacities from 20 milliliters to 2 dram. You can see the different sizes here. Temperature control is either by a hot plate stirrer, and we all have hot plate stirrers, or if you need low temperatures, we have a temperature controlled base that you can connect to a recirculator chiller to get to those cryogenic temperatures if required. But it has a wide temperature range, and it also has a wide number of ports, so we can sample and add, and we can also reflux. So it has most of the capabilities that you would expect from a round bottom flask, but now we're adding increased mixing potentials with overhead stirring. You can see from this image here how it sits on a traditional magnetic stirrer. We're not using the magnet for stirring traditionally. Now we're adding the addition of an overhead, a magnetically coupled overhead stirring system. This is directional. We can change the speed of our propellers. We can reverse, and if we're using solids, that can help us in certain situations. We can also run under inert conditions. As I said, the vessels that we have come with a range of different sidearm configurations, and we can even reflux on these systems here. So that's all I was going to introduce, all I was going to say about the mini spin. You've seen some of the data presented by Mark that shows that this can affect mixing when you need increased mixing profiles within your chemistry. And certainly for viscous media and for where you have applications where you don't want to damage solids in material construction, for example, this plays a good part. So I'm going to finish everything there. Just to say that we've seen a very nice introduction to Kineticolor's non-invasive computer-driven software, and we can see how that can impact our understanding of time and spatially resolved kinetics and mixing data. And I've given you a brief introduction to our new overhead stirring system for small scales, which previously hasn't been available. So what I'm going to do now is open the floor to questions. Hopefully, we have a nice range of questions entered into the chat function. If you haven't entered anything yet, please type that in. My colleague will be reading out the questions, and hopefully we can answer some of those and give you some more insights.
One of these is wondering if the cameras will work if the vessel is jacketed.
That's a great opening question. So if I've got this assumption wrong, please do correct me. But if we're talking about a single or double jacketed vessel with oil or thermal liquid circulated to control temperature, and it remains a transparent vessel, absolutely. That is materially not different to a beaker as far as the software is concerned, so long as you can point your choice of video camera at that process and get the video data out, be it an MP4 or an MOV file or something equivalent to those, then you can still go through the process of video goes in to Kineticolor and kinetics of the bulk comes out the other side. In relation to that, going further, if it is a jacketed vessel or indeed a non-transparent vessel, we are working with a number of collaborators who, for example, have equipment with cameras already embedded in the hardware. So they're looking for opportunities to turn their existing video data, which exists simply for electronic lab notebook purposes, take those data and turn it into more powerful information. So in other words, rather than just having a video recording exist for the sake of it, then use those video data as input to derive more information, be it on mixing or the colour profile, or something about the spatial distribution of colour across that reactor. So I hope that answers the question on jacketed vessels.
Wonderful, thank you. So the next question, in the videos, we're constantly showing a liquid dye and a liquid medium. Are there options available, or is it possible to do solid liquid mixtures such as powders in a heterogeneous reaction?
Yes, absolutely. As a key point here, remember that if you can see it by eye, if you can describe it and write it down, the answer is yes. It doesn't matter if we're talking about liquid, solid, solid. If there is an apparent change in colour or distribution of colour or some other visible phenomenon taking place, that's what can be quantified. When you record the video, there's no way for us to tell the camera or the software that it's a particular process. Of course, there are models where you can build in this context, but that's the provocative way of thinking about it. As long as you can get a video, then you can try to quantify that change. What I'm putting in the chat is an example of one of our earliest mixing publications in OPRD, where there's an example of quantifying mixing times for suspended solid in liquid and looking at the settling time of that solid in the liquid. In a later publication, we went on to show how we could do that in a parallel sense for looking at 4 processes where there was a solid impurity inside a liquid bulk, and we stirred those mixtures and looked at the settling time of that solid impurity as a measure of the quality of that given material.
Fantastic, thank you. Okay, so next question. On the computer vision itself, how sensitive is the software to movement of the reaction jar itself? For example, if the entire jar is shaken with a defined amplitude to induce mixing, can the software still accurately analyze the mixing process?
Yes, that's a great question and something we've thought about a lot ourselves. So again, it's if you've got a video camera that allows you to see that full field of view where you can capture the amplitude, then some of the algorithms within Kineticolor will help you average that change of color over time. So you see the overall impact, even although there may be some oscillating noise induced by the shaking effect of that mixer itself, you can still capture the overall trend. We've also seen this in a paper that we have under peer review at the moment, and this ties in with the earlier question on does it need to be liquid? We've been looking at characterising solid material degradation using Kineticolor, and in that case it wasn't oscillation through a shaker, but we had oscillation through a light source that was by design turning on and off whilst we monitored the process. And what we saw there is that a main trend could be captured, and superimposed onto that was the oscillation of the light turning on and off. Sorry, and all of these data are available in Excel and other raw formats. So it's relatively routine then to decouple the main trend from something that may be oscillating over the top.
Wonderful. Okay, thank you, Mark. Next question. There are lots of questions, which is fantastic.
Excellent.
The delta E is resulted from a single point measurement. Could this apply to area measurements? And how do you deal with the in-between colours? Does the curvature of vessels affect the accuracy? And how was the degree of colour related to conversion? There's a lot to unpack in there.
There's about 4 or 5 questions, all of which are really legit and excellent. So let me try my best to unpack, and we'll revisit the later ones should I forget them. So delta E is a single point measurement, first of all. That's not strictly true, but understandable based on what I presented. So what I shared was some examples where we might pick a particular region of interest, and we captured the delta E, the colour change within that region. Remember, you can then choose multiple regions, so you can get that delta E information from other parts of the same video process. Where we have tried to treat it as a strict point measurement is when we're comparing what is the delta E at this part of the video where a probe also happens to be sitting, because a probe by design is more of a point measurement, not spatially resolved, whereas the video data are inherently spatially resolved. There was then a question about in-between colours. So I have shown delta E as a real workhorse metric that in a colour agnostic sense captures the change over time. And if you're mainly interested in the kinetics or when things plateau or what the rate is, something like delta E is a really intuitive, easy metric to use to capture everything that's going on in the bulk. However, under the hood, and what I've not shown today, is that what also comes out of Kineticolor is all the individual colour channel information for RGB, HSV, LAB, all of these things that are complementary to delta E. So there are other ways to look more specifically at given colour changes when they appear and when they disappear over time. So for example, we had a recent publication looking at gas release kinetics from carbon monoxide surrogates. And in that case, we used a particular carbon monoxide sensor, which changed from red to yellow when carbon monoxide was detected. And in that case, delta E was sufficient, but we could go better by looking at the specific hue parameter for what the numbers were on changing from red to the specific yellow that we cared about. So delta E is great, but there is a lot more in there that gets you to those intermediate colour changes. So the other half of those questions, Kirsty, if you could remind me what I might have missed there.
Yeah, bear with me. Just scrolling through all the other questions. So does the curvature of the vessel affect the accuracy?
I now remember the other question as well. So coming to curvature first, if you're doing a series of experiments with the video camera pointed at those experiments and you want to compare the outputs from those videos, so long as you are consistent, you still get usable information of comparing reaction A to reaction B. So if for a highly curved vessel, make sure, for example, that you're choosing the same area, the same region of interest as you move from experiment to experiment. And one of the ways that we build that into Kineticolor, having been asked by our industrial colleagues, is that you can load up the settings from a previous analysis so that you are collecting information from the new experiment with the same parameters as the previous experiment. So in other words, you don't need to worry too much about curvature so long as you're consistent about where you're picking the colour data from in the video. The other question that was asked that I now remember is how do you couple, or how do you understand the correlations between the colour data and the progress of the reaction? And if you look at any one of our recent publications, we lean on specific statistical tools so that we can ask the question, how do our colour data relate to the current process monitoring tool of the day? So, for example, we looked at a process to understand solid phase peptide synthesis, and that we did that because it was important to try to get an ex situ measure of the change of colour over time. And sampling those processes is inherently difficult. But what's normally done in that field is to, for example, measure what's left behind in the solvent, or measure the cleaved growing peptide from a resin using HPLC. So it was important that we conducted our study looking at how our colour change metrics correlated with HPLC. And in that way, we could show, and have done in many studies now, that we give evidence to say that the story of the reaction over time by colour is the same story of the reaction over time by HPLC or NMR, or whatever the other metric of choice happens to be, depending on the chemistry context. So there are ways to do that. They are really the receipts of validation in all of our peer-reviewed work that's allowed us to take Kineticolor out of the academic world and do our very best to commercialise the solution for both academia and industry.
Fantastic. Are you ready for more questions?
Always.
Yeah.
I'm very grateful there's so many.
Yeah, it's great. Is there any capacity for reaction monitoring using hyperspectral imaging with Kineticolor?
Yeah, this is a really timely question. So the short answer is yes. We started this whole story by setting ourselves the challenge of make a software that works for anyone with any camera looking at any process. We've spent most of our time in the past 5+ years looking at any visible process. So lots of processes where it's, as we mentioned earlier, traditional wet chemistry, liquid-liquid mixing, solid-liquid mixing, entirely solid-based chemistries for materials design. And there's been a rich vein to tap into understanding how we can use off-the-shelf commercial cameras to look in the visible range alone and capture this valuable information of how the bulk changes over time. What we're doing now, and again, what we're just about to publish on, is, for example, looking at how we can take out a traditional visible range camcorder, let's say, and use a slightly more sophisticated machine vision camera, which in one hardware box has both a visible sensor and a near infrared sensor. And what we're showing firstly is that cameras like that remain compatible with Kineticolor, and the fact that you're getting different sensors capturing different parts of the visible and beyond visible spectrum, you get complementary information from each regime about what's going on inside that vessel. So we analyse 2 videos rather than 1, and each video is capturing information from either the visible or the near IR side of the spectrum. So we are now starting to show that we go beyond visible. It does not need to be what you see by eye anymore. And the natural extension of this is looking at cameras that are either sensitive to the UV, or, as the colleague in the question rightly mentions, even more sophisticated hyperspectral measurements.
Wonderful. Okay, so that's answered another of the questions that we have in
Very
there.
good.
Next one is, how does it work with a volatile solvent, as evaporation of those solvents affects the process?
Yes, so
mostly if caps are made of plastics, which after using for a few experiments at high temperatures, they don't work well later.
yes, so what I'm putting in the chat for this question is an example of one of our papers. I mentioned this earlier, looking at the kinetics of gas release from carbon monoxide surrogates. And the supporting information of that paper is an example of our team facing the same problem, where the original design of that experiment used DCM for various reasons early on. And we found that over time, the DCM was evaporating. That was influencing the concentration and therefore the colour and so on. The first important thing to do, which allowed us to exemplify another bit of what Kineticolor does, is use the shape function to analyse the solvent height over time. So we could quantify and evidence through the video data at what rate the evaporation was taking place. And what that then helped inform was a move, in this particular case, to DCE, so dichloroethane, as a higher boiling near equivalent of DCM in terms of solvent profile. And that then we could evidence did not evaporate to the same rate, and therefore meant that the measurements of colour change over time were more reliable for the comparisons we were trying to make between different carbon monoxide surrogates. So I'd say in answer to that question more fully, awareness of evaporation is the first thing. There's many other types of processes where the kinetics are not taking place in a stable regime over time. The medium itself is changing, and therefore the kinetics and maybe even the rate laws themselves are changing over time. Even before Kineticolor, our team faced an example of this when we were looking at salt degradation for methylation chemistries. And in that case, we were going from highly polar reaction medium with charged species to less polar reaction medium with neutral species. And the fact that the polarity of the medium was changing over time actually complicated the kinetics and changed the kinetics over time thanks to the medium itself changing. So it's a really interesting thing to keep an eye on. If you've got evaporation, it's not just the colour that's changing, there may be other things changing in those chemistries as well.
Fascinating. What else have we got? How fine size can be observed? How does it deal with oiling out videos?
That I would love a follow-up conversation on to make sure I understand this properly. But for the sake of today's audience, I can focus on the point of fine size, because it gets back to the fact that what we're talking about here is a software product, not a camera hardware product. So if you're worried about fine size, or you're challenged by the definition of the video, or you need to look at really zoomed in areas or particulates in a microscopic regime, so long as you've got access to a video camera that is capable of capturing information and that level of resolution, then the video is a video is a video. It remains compatible with Kineticolor. So to give you another example, a lot of what I've shown today has been through using webcams or camcorders or phones to, in a zoomed out sense, look at a large reaction vessel, or look at the fullness of a vial. But we've also got projects going on where we've got more microscopic setups where we're looking in a very zoomed in sense at what's going on inside a petri dish. And that's in relation to some electrochemical projects that we're running at the moment. So when we move from looking at large scale tank reactors to moving to looking at reactions that are taking place in a petri dish or even smaller, it's not the Kineticolor software that's changing. We are simply changing what camera is fit for purpose on moving from one project to another.
That makes complete sense.
I hope so.
Right. I mean, we've only got a few minutes left.
Okay.
But there was a question that came in earlier. Can Kineticolor monitor a live video input and output signals for controls? For example, add a reagent, wait until mixing is complete, take a sample.
Yes, so capturing the live part of that there. So when Kineticolor was first developed, we did so deliberately as a post-processing tool. So think of it like using your favorite NMR software to understand what was going on in the NMR experiment. You know inherently that NMR experiment has been run, and you're looking in a post-processing sense at the data after the fact. So Kineticolor was like that to begin with. You would record the video, you would then take that video to the software and analyze it afterwards. That remains the core value add of the software. But we do have in beta at the moment an ability to plug and play, where you can put the camera of your choice into the computer on which you're hosting Kineticolor software and capture those data as you are figuring out what the setup looks like to get some quick feedback, or if you want to be able to look at things in a staged sense. The final thing I'll say about a staged process where you might be looking at one thing happening then another, this is the other thing we've made sure we've built into Kineticolor, is an ability, like you would expect of any video analysis platform, to trim the video to the point in time that you care about. So we've got projects running at the moment where we might, for a single video, look at the charge of a solid and watching it dissolve. We might then watch the process of how that mixes as another reagent is added in. We might then look at evaporation and so on. So you get phases and regimes of what's going on. And it doesn't mean you need to analyse the whole video. You can analyse that portion in time that you care about most. And if you then decide later that you want to go back to it and analyse another part, that's the beauty of having the raw video. You can analyse it and put it through the software as many times as you want to try to extract all the information that's important to your understanding or optimization.
Amazing.
Fantastic.
Thank you so much, Mark. I will
Pleasure.
hand over to you gentlemen just to finish up because we are pretty much out of time.
Yeah, that's fantastic. Thank you very much for all of your questions. You've kept Mark on his toes, and thank
Absolutely.
you for. And if you have any further questions, you can field them via us or directly to Mark himself. By listening to those questions, that has piqued a lot of interest, and you can see that it's a very versatile, very informative software. So again, thank you for joining us. Look out for the next webinar. Hopefully you've learned something today. I have. The Kineticolor offers a real deep understanding of your reaction mixing and kinetic data. And you can see the developments that are going on in the background to increase this further. You can also see from Asynt's viewpoint that with better mixing control on small volumes, that can enhance your chemistry as well. So if you need any further information from us or Mark, please get in touch. Again, thank you for joining us today, and we'll see you next time. Thank you.